Hello everyone, I am A. Rajkumar, Assistant Professor, Department of Chemical Engineering, Hindustan College of Engineering and Technology. In this presentation, we are going to discuss about material balance in chemical process calculation and its introduction. Basic principles of material balance. Material balance is an expression of law of conservation of mass. According to the law of conservation of mass, mass neither can be created nor destroyed, but it may undergo phase changes. That means mass can be undergoes transformation or transfer from one phase to the another phase. Also it goes to the chemical changes. In many industrial process, material balance provides an exact accounting of all the materials that enters into the system and leave this or any changes happening inside the system. So the basic fundamental principle for the material balance is the law of conservation of mass. According to the law of conservation of mass, we are deriving the material balance. So this is the expression for the law of conservation of mass. Materials input into the system minus material output from the system plus material generation within the system minus material consumption within the system, which is equal to the accumulation of material within the system. In many unit operations, material generation within the system and material consumption within the system is not happening. That means it is only happening in the unit process where there is a involvement of chemical reaction. In unit operations, material generation and material consumption becomes zero. So in that particular case, we are eliminating these two terminology. In material generation, we are giving the plus notation. That means there is an increment of mass within the system. So that is why we are giving the plus notation. In material consumption, we are giving the negative notation. That means material is consumed during the reaction. So the quantity of the quantity within the system is decreasing. Before going for the material balance, we need to understand the different process classification. The first classification is batch process. In many batch process, feed is charged into the process and the product is removed when the process is completed. So during the process, there is no input into the system and there is no output from the system. That means there is no mass fed or removed from the process during the operation. Most of the cases, batch process is used for the small scale production. For example, pharmaceutical industry. The second classification of process is the continuous process. It is exactly opposite to the batch process. That means during the process, there is a continuous input of the mass into the system and there is a continuous output from the system. That is continuous process. It is mainly used for the large scale production. Most of the process are the continuous process. And the final classification of process is the semi batch process. So it is neither batch process or nor continuous process. That means during the process, one part of the reactant can be fed into the system and the product can be only removed after the process completion. That means, yeah, one of the reactant is continuously fed into the reactor and one reactant is already fed into the reactor, but during the process there is no product withdrawn from the system. So that is the semi batch process. Operation of continuous process. Any process can be classified into two types. One is steady state, another one is the unsteady state. In steady state process, all the variables like temperature, pressure, volume, flow rate, etc. do not change with time. There is a minor fluctuation can be acceptable, but the most of the time the variable parameter is not changing with respect to the time. In unsteady state, all the process variable is changing with respect to time, in particular in mass flow rate. So these are the two operations of continuous process. So based upon the process classification and operation of continuous process, we are applying these to continuous condition into the fundamental principles. That means we are assuming all the unit operations are under steady state. That means accumulation is constant. So in the basic fundamental expression, we are eliminating the accumulation with respect to time. So accumulation is zero. In other cases, based upon unit operations, that means there is no reaction, that means material generation and material consumption is become zero, so it can be eliminated from the law of conservation of mass. Finally we will get the simplified expression of law of conservation of mass, that is input is equal to the output. That means whatever the quantity entering into the system will leave the system, the quantity will not change. It may be split into two stream or many stream, but the final overall quantity of the output is exactly equal to the overall quantity of the input. Methods of solving material balance problem. So there are three methods available for solving the material balance problem. One is tie element approach, second one is the inert material approach, third one is the simultaneous equation approach. The first one, tie element approach or key component, is the material which enters or leaves the system in a single stream, or one which enters and leaves without any change. An element, compound, or an unreactive mass like the ash present in a coal can be treated as a key component. That means the tie element will not change the quantity during the process. Whatever the quantity enter into the system will leave the system without any change in the overall quantity of that particular compound. That is tie element approach. In second method, inert material approach, the substance present in a feed material will not generally reactive, it is inert to the reaction, so inactive with respect to the chemical reaction. So during the combustion reaction some material will not reactive with the reaction, so that is based upon this inactive component we are deriving the material balance problem. So that is inert material approach. The third method is the simultaneous equation method. So we are having n number of equations to find out the n number of unknowns, so we are developing the n number of equation with equal to the n number of unknowns. By solving these n number of equations we are identifying the n number of unknowns. So these are the simultaneous equation method. Now we are going to discuss about one important unit operation that is available in chemical engineering, that is distillation. So what is the definition of distillation? So distillation is the unit operation which is used to separate the mixture of liquid components based upon their boiling point temperature difference. So this is the definition of distillation. So we have done many distillation experiment in a laboratory level. So this diagram represent the laboratory level simple distillation setup. So in right hand side we are having the mass balance over a simple distillation. So we have feed, so that is expressed in F. So the overall quantity of feed is F, comma X suffix F. So that is the mole fraction of component A present in the feed mixture. In top of the distillation we are collecting the distillate, so that is the evaporated component, vapor component that can be condensed into liquid form. We are collecting as a distillate, so that is top product. So the overall flow quantity of the distillate is the represented as D, capital D. XD is the mole fraction of component A available in the distillate. In bottom of the distillation column we are collecting the bottom product or residue. So it can be the overall quantity of the bottom product can be expressed as a capital B, and mole fraction of component A present in the bottom product can be expressed as a XB. So the overall material balance for this distillation column is the F is equal to D plus B. That means according to the law of conservation of mass, the input is equal to the output. So the input to the system is feed F, and output from the system is distillate and bottom product. It is represented D plus B. So this is the overall material balance expression for this distillation setup. So next we have to write the component material balance expression for this distillation with respect to component A. So F into XF is the amount of material present in the feed mixture. Amount of component A present in the feed mixture is equal to amount of component A present in the distillate is written as D into XD. So D is the overall quantity of distillate, XD is the mole fraction of component A in the distillate, plus Amount of component A present in the bottom product is expressed as B into XB. B is the overall quantity of bottom product and XB is the mole fraction of component A in the bottom product. Now, based upon the material balance expression derived for distillation unit, we can solve one example problem. So there is a continuous distillation column where we are extracting the solvent which has the feed flow rate of 200 kilomole per hour. It has the 10 percentage of ethyl alcohol and the rest is the water. That means 90 percentage is water. During the distillation process, we are collecting the distillate. So the overhead product has the 89 percentage of alcohol and the remaining 11 percentage is the water. And the bottom product has 0.3 percentage alcohol, remaining 99.7 percentage is the water. So the aim of the distillation to separate the ethyl alcohol present in the water, so that we can use the extracted or distillated ethyl alcohol from the distillation for the extraction unit. Material balance problem, first we need to write the basis, so that is very important. So the basis for given problem is 200 kilomole per feed of liquid mixture, so that is a mixture of ethyl alcohol and water. So we can say F, D and W can be the flow rates of feed, distillate and residue respectively. X of XD, XW be the mole fraction of the ethanol in the feed, mole fraction of ethanol in the distillate and mole fraction of residue in the bottom product. So we know in the problem statement the overall flow rate of feed is given as 200 kilomole per hour. The mole fraction of ethyl alcohol in feed is 10 percentage, that means 0.1, and mole fraction of ethyl alcohol in distillate is 0.89 and mole fraction of ethyl alcohol in bottom product is 0.003. So we know the overall material balance expression for this distillate is F is equal to D plus W, and component material balance expression for this distillation is F into XF is equal to D plus XD plus W into XW. So in overall material balance expression we have to substitute the feed value, that is 200 kilomole per hour. In the second equation, that is component material balance expression for ethyl alcohol, so we have to substitute the given mole fraction value, so that is written here 0.89 into D plus 0.003 W is equal to 200 into 0.1 is equal to 20. So by solving these two expression, overall material balance expression and component material balance expression, we can get the flow rate of distillate as 21.87 kilomole and flow rate of bottom product as 178.13 kilomole. So this approach actually is the simultaneous equation method. So finally, so what is the amount of alcohol wasted during the process? So that means alcohol present in the residue. So we know the overall quantity of overall quantity of residue as 178.13 kilomole, and we know the what is the mole fraction of alcohol in the bottom product. So that is 0.003. So by multiplying these two, we can get the what is the quantity of alcohol wasted in the distillation process, that is 0.5344 kilomole per hour. So therefore to make up the alcohol required per day, so we are multiplying with 24 into 46 is equal to 589.98 Kelvin. So per day we have 24 hours. The molecular weight of ethyl alcohol to convert kilomole into kg is 46. So finally we are getting the required amount of ethyl alcohol to make up the process in terms of kg is 589.98. Thank you. So these are all the material balance over distillation process.
Thank you. I hope you all understand.